Hello viewers, how are you? Welcome to my channel Physics with Rams. So today we are going to discuss about a kinetic theory of gases. In this chapter, first of all we are going to discuss about Boyles law. In Boyles law, we are going to discuss about the variation of pressure pressure with respect to volume. As we know that pressure is inversely proportional to volume. As the pressure increases, volume decreases. As the pressure decreases, volume increases. So based on that, here we can represent that PV is equals to constant. Why? Because pressure is inversely proportional to volume in the case of Boyle's law. The second law is Charles' law. Charles' law. You can also call it as Charles' law. In the case of Charles' law, we know that pressure remains constant and volume is directly proportional to temperature. Here, as we observe that as the volume increases, temperature increases. As the volume decreases, temperature decreases at a constant pressure. So based on that, here we can represent that V is directly proportional to, or we can also represent it as V by T is equals to constant. So here, as we observe that now we are going to discuss about gay-lussacs law. In this law, here we consider volume as a constant and pressure is directly proportional to temperature. As you observe this equation, here observe that as the pressure increases, temperature increases. As the pressure decreases, temperature decreases at constant volume. So now based on that, here we can represent P by T is equals to constant. So here we can represent it as a P1 by T1 equals to P2 by T2. P2 by T2. Here, as we observe this Charles' law, here we can represent that V1 by T1 is equals to V2 by T2. These are the equations given in the case of Boyles law, Charles' law and gay-lussacs law. Take a screenshot, we will continue. As we observe that at STP, standard temperature pressure, where S represents standard, T represents temperature, and P represents the pressure. The pressure is represented as 1 atmospheric pressure, and we know that the value of 1 atmosphere is 1.015 into 10 to the power of 5 Pascal, whereas the volume is being represented as 22.4 liters and temperature is being represented as 0 degrees Celsius, or we can also represent it as 273 Kelvin. So here when we consider a gas at STP, we represent the gas in terms of moles, where 1 mole is equals to number of represented as a number of molecules in the mole, whereas number of molecules in a mole can be represented with a Avogadro number. And we know that the Avogadro number is represented as n suffix a, and the value of n suffix a is 0.6.023 into 10 to the power of 23 per mole. Take a screenshot, we will continue. Where we know that the mole is being represented with mu, where mu equals to n by n suffix a, where n suffix a is Avogadro number, mu is the mole, number of moles, and n is the number of molecules or number of molecules. So based on that we can represent it as n equals to mu into n suffix a. Suppose if we consider 1 mole of gas, mu equals to 1 mole, then here we can represent the n is equals to 1 into n suffix a. So here as we observe that n is equals to n suffix a in the case of 1 mole of a gas, whereas similarly we can also represent mu is equals to m by m suffix a, where m suffix a is atomic mass, m is the mass of the given gas, and it's a atomic gas, atomic mass. So here mass of a given gas is represented as mu into m suffix a. So now we are going to discuss about ideal gas equation based on this STP condition. Take a screenshot, we will continue. Now we are going to discuss about ideal gas equation. Ideal gas equation. Come to the case of this ideal gas equation, it is being given based on pressure, volume, and temperature. As we observe this equation here in the case of Boyles law, we know that pressure is inversely proportional to volume, and in the case of Charles law, volume is directly proportional to temperature. So now combination of these three is being represented as ideal gas. In the case of ideal gas, the expression is being represented as PV by T, which is equals to constant. Come to the case of this. Here observe that the PV by T is a constant, whereas PV by T is being represented as mu into R, where R is a universal gas constant. Universal gas constant, and the value of R is 8.314 joule per mole per Kelvin. Here P is a pressure, V is a volume, and T is a temperature. T is a temperature, R is a universal gas constant. and we know that mu is nothing but a number of moles. And here, as we observe this equation, here we can represent that PV equals to mu RT. From this, the pressure can be represented as mu RT by V, where we had seen that mu is equals to N by N suffix A, as well as we also had seen that mu is equals to M by M suffix A. So now we are going to replace mu with N by N suffix A. Before going to discuss this, just take a screenshot. Mu is equals to N by N suffix A. From this equation here, observe that P is equals to N RT by N suffix A into V, where we know that the number density can be represented as small n equals to capital N by V, where small n represents the number density, number of molecules by volume, given volume. Then the pressure can be represented as a PV equals to small n RT by N suffix A. We know that K suffix B is nothing but a Boltzmann constant, and it is equals to universal gas constant by Avogadro number, and the value of Boltzmann constant is 1.38 into 10 to the power of minus 25 joule per mole Kelvin. So now here, based on this, as we substitute that pressure is equals to N into K suffix B into T. This represents the expression of pressure in terms of number density as well as the Boltzmann constant. Whereas when we try to represent the same expression in terms of mass, we know that N is equals to mass of the given gas by atomic mass. From this, as we substitute this, here N is nothing but a number of moles mu. So here the pressure can be represented as number of moles small m RT by M suffix A into V, which is equals, we know that mass per volume is nothing but density equals to mass by volume. So as we substitute here, we get a rho RT by M suffix A. This represents the expression for pressure in terms of density in the case of ideal gas equation. Take a screenshot, we will continue. A gas. So now here, as we had observed that we had considered a container along x, y and z axis. Observe that this container consists of a single gas molecule. So here, when we consider that initially the gas molecule is at point A, it moves towards the wall, it collides with the wall and returns back to the new point B. Now based on that, here we are going to represent the condition. Observe that the molecule is moving along the x-axis from point A towards the container. As it collides with the wall of the container, it returns back to the point B with the same velocity along the opposite direction. So now here, now we are going to represent the expression of momentum. When we observe that when it is moving from point A, the momentum is being represented as mass of the molecule into velocity V suffixes. When it returns back, the momentum is being given as minus mv suffix x. Why? Because it is returning back along the negative x direction. Then a change in momentum is given as minus mv suffix x minus mv suffix x, final momentum minus initial momentum, which is equals to minus 2mv suffix x represents the change in momentum for this gas molecule when it has collided with the wall. So now here when we consider the magnitude for this expression, delta of mod of delta p equals to 2mv suffix x. Now we are going to consider the expression for speed. We know that speed v equals to distance by time. Here from this distance can be represented as speed into time. So here as we observe this expression, now let us consider volume. As we observe that volume equals to area into distance. Here the distance in terms of velocity along the x-axis is being represented as a into distance is v suffix s into change in the time delta t. Sure, then we can represent the number density, where we know that the number density is given as small n equals to capital N by V. Then capital N is equals to small n into V. Observe that volume is being represented as A into V suffix S into D. Then here then number of molecules equals to number density into area into V suffix S into delta T. So here observe that half of the molecules, if we consider number of molecules, as we had considered a single molecule, if we consider number of molecules, then half of the molecules will reach to point B. Then half of the molecules in terms of n can be given as n into A into V suffix S into delta T by 2. This represents the half of the molecules which has been written back. Then the total momentum in this condition is given as n into A into V suffix S into delta T by 2 into delta P. Sure, delta P. So now here based on that observe this the expression can be represented as n into A into V suffix S into delta T by 2 into, observe that the momentum is being represented as 2m into V suffix S, 2m into V suffix S. Observe this 2 and 2 gets cancelled. So here we get n A V suffix x square into delta T. This represents the total change in momentum for number of molecules. Just take a screenshot, we will continue. Presented the change in momentum as a delta P of net is equals to n A m into V suffix x square into delta T. Then the force, net force acting in the case of gas molecules is given as a change in the net momentum by delta T. So this represents the expression for force. Then here as we substitute the value of change in the momentum, n m A V x square into delta T by delta T. Observe that delta T gets cancelled, and here then the force can be represented as n m A V suffix x square. Here this represents the expression for force, whereas the pressure is being represented as force acting per unit area. So here based on that the force is being given as n m A V suffix x square by A. Observe that A gets cancelled. So here the pressure is being represented as n m into V suffix x square. This represents the pressure acting along the x-axis. So here now we are going to represent the pressure in terms of density. We know that density equals to mass by volume, and the number density can be represented as N by V. So as we multiply M on both sides, here we can represent it as N into M is equals to capital N M by V, which is equals to density. So by replacing Nm with rho, the pressure can be represented as P equals to rho Vx square. This represents the pressure acting along the x-axis. So now here we are going to represent the pressure along the three-dimensional axis. Why? Because we had considered the container along the three-dimensional axis. As we represent that V square equals to velocity along the x-axis, velocity along the y-axis, and velocity along the z-axis. Here as we observe that velocity along the x-axis is equals to velocity along the y-axis as well as velocity along the z-axis. So now here based on this we can represent that Vx square is equals to 1 by third of V square. As we substitute this value in the expression of pressure, the pressure expression can be represented as P equals to 1 by 3 rho V square. This represents the expression of pressure in the case of a container containing with gas molecules. So now here as we observe that V square equals to 3P by rho. So as we observe this V equals to root of 3P by rho. This represents the RMS speed of the gas molecules. Take a screenshot. I hope that you liked my video. Please share this video to your friends and don't forget to subscribe my channel. Thank you.